Swayam Prabha. Digital India. Educated India.
Hello. So in the last lecture, we had discussed the derivation of the equations for a transmission line. The transmission line was a model based on which we would model any distributed element like waveguides, coaxial cables. So for this lecture, we will further expand our discussions of the transmission line, and we shall see some special cases and also discuss some more concepts. So let me share my screen first. Okay, so the equation for we started with transmission line. So there is a load ZL connected at one end. Suppose at a distance d from the load end, we want to find out the input impedance. And the expression for the input impedance is given as now here we are assuming that this transmission line is lossless. Okay, so we had found that this is this input impedance is periodic with respect to beta d. So whenever beta d changes to beta d plus pi, we get the same value of Zn. Similarly, now this can also be expressed that if beta d changes to beta d plus pi, then beta is equal to 2 pi upon lambda. Okay, so beta d is equal to 2 pi upon lambda times d. So if beta d increases by, so beta d plus pi is equal to 2 pi upon lambda d plus pi. Okay, so this is equal to pi 2d upon lambda plus 1. Okay, so this in turn, we can say that suppose now I take d as common. Okay, so what does this mean? So it means that or let me do it in a different way. Suppose I have d plus lambda by 2. Say the distance d changes to d plus lambda by 2, then what is beta d plus lambda by 2? This is equal to beta d plus beta lambda by 2, which is equal to beta d plus 2 pi upon lambda into lambda by 2. So this is equal to beta d plus pi. So in other words, increasing the value of d by lambda by 2 is the same as increasing the value of beta d by pi. Okay, so that's why if beta d is periodic in pi, then the same effect, in other words, the value of z in d will be equal to z in d plus lambda by 2. So every half wavelength, the impedance will repeat itself. Okay. So let us see what is some special cases. One of the special cases is a shorted transmission line. Z of D for such a line will be given as okay. So if for a shorted line ZL is equal to 0, so this in then implies Z of D is equal to J Z0 tan of beta D. Okay, so this is what the input impedance reduces to. So a shorted line, is like this, and then there is a short, there is a solid short here. So for this line, the Z in of D is given by this expression. Similarly, we can have a open transmission line. So for an open transmission line, ZL will be equal to 0 and Z in, this should be Z in, Z in of D will be equal to, sorry, I made it, this should be ZL is infinite, so it's like this. This is open, and we are trying to find out the input impedance here, and that expression is given by, okay. And one more case, special case, is when we have what we call a matched load. For a matched load, we have ZL is equal to Z0. So the load is same as that of the characteristic impedance. In this case, So the input impedance at whatever length you consider is always equal to Z0. So for a matched load, it's like as if this entire length does not exist. It's almost as if the load is directly connected to the input. Okay, so it's like this. So suppose the characteristic impedance here is Z0, and this is almost as if I just have the load directly connected to the input. Okay, now for a shorted transmission line, coming just back to the shorted T line, is the shorted T line and open T line, we will be using it a lot. If we see, first of all, if we go back to the expression for the input impedance of a shorted transmission line, we see that for a lossless shorted transmission line, the impedance is purely reactive. There is only the imaginary component. There is no resistive component to the impedance. So if we plot the imaginary component versus so So in the x-axis we have D, in the y-axis we have imaginary K. Okay, so this is how this, if we plot the imaginary value of the Zin with respect to D, this is what we get. As we can see, and what I said, the input impedance will be periodic with respect to lambda by 2. You see, for every lambda by 2, the value repeats itself. Okay, and the value can be both even though it is imaginary, it can be both, impedance can be both capacitive or inductive. Okay, so in this region it is inductive when the value of imaginary part is positive, and in this region it is capacitive. Okay, so I would like you to derive the same graph for a I would like you to derive the same graph for a open transmission line, open stub. We also call an open transmission line as a stub, open stub. So this is for so this whole diagram is for a shorted transmission line. Similarly, I would like you to derive the graph for a open transmission line. So one other important case is what we call a quarter wave transformer. So what is a quarter wave transformer? A quarter wave transformer is transmission line. So if we draw the quarter wave transmission line transformer, so this symbol is also the symbol of a transmission line. A transmission line, as I mentioned before, is characterized by two components. One is the characteristic impedance, or CI, and the other is the beta D, or electrical length. Okay. Now, if we calculate the Zin L, so the total length of this transmission line is L. By the way, this beta D is also sometimes referred to as theta. Okay, these two terms are sometimes equivalent. So if we try to calculate, so what will be the value of Zin L? Again, if we use that formula, beta L. Okay, so let me erase. It should be beta L, because now we are considering the complete length of the transmission line. So it should be beta L. Okay, so then this upon okay, now beta L here is pi by 2. So if beta L is pi by 2, then L is equal to pi by 2 to 1 upon beta, which is equal to pi by 2 into lambda upon 2 pi, and this is equal to lambda by 4. Okay, so now substituting beta L equal to pi by 2 here, what do I get? Zin of L will become Z0 square upon ZL. So what do we see from this equation? Note that Z0 is always positive, isn't it? That's what I mentioned in the last class, that we don't want Z0 to be frequency dependent. If the Z0 has a imaginary component, then it inevitably has a frequency dependence, which we don't want. That's why we want Z0 to be positive. Okay, Z0 to be real, I beg your pardon. So Z0 is always real, and if ZL is resistive, then Zin is also resistive, and Zin is proportional to 1 by ZL. That's why this quarter wave transformer is also called an inverter, because it inverts the load impedance. So because the input impedance, if I increase the load impedance, then my input impedance will decrease. So this, because of this inverse relationship that exists between the input and the load, it is also called an inverter. Okay, in fact, it is, as we shall see, a quarter wave transformer is also used for impedance matching, as we shall see. And if we want to, for example, if we have a load RL, say like this, and say we have to obtain an input impedance of Rg, then what should be the value of the characteristic impedance of a quarter wavelength transformer? So instead of writing quarter wave transformer, I just write it as lambda by 4. So the value will be Rg is given by Z0 square upon RL, and from here we get Z0 is equal to RG times RL square root. Okay, this is the relationship. This is the value of the characteristic impedance of the quarter wave transformer. Now I would like to mention one thing, that the quarter wave transformer is quarter wavelength long only at a particular frequency. So when I say lambda by 4, it corresponds to that frequency. So for example, if we have a quarter wave transformer at 1 gigahertz frequency, it will not be quarter wave transformer at 2 gigahertz frequency. So this is important. Please understand this. A quarter wave transformer is a quarter wavelength long only at a particular frequency, not for all frequencies. Okay, so one important concept or one important parameter that we need to know, and which is very important in microwave engineering, is what is known as reflection coefficient. So what is reflection coefficient? So reflection coefficient is given by, suppose again if we consider a transmission line and say I consider a distance x, but x is from the source, not from the load, and say at this point the input as a function of x, input impedance as a function of x is Zin of x. Say the amplitude of the wave traveling in the positive x direction is v plus x, and the amplitude is v minus x for the wave traveling in the negative x direction, and say our load is ZL. Okay, so this is our transmission line. This part is not the transmission line. Okay, this is just a connection. The main transmission line is only between these two parts. Okay, I have to consider this part because I need to connect it, right? I need to connect. It's like this load is connected to this point, but I have to use a straight line so as to show the connection. Okay, so now the reflection coefficient at this point, it is usually represented by capital gamma, and capital gamma of x is given by the amplitude of the wave traveling in the negative x direction upon the amplitude of the wave traveling in the positive x direction. Now we know from the solution for the transmission line equation that v minus of x is given as v minus of 0 e raised to gamma x. Now here if I am using gamma, small gamma, so this is capital gamma is used for reflection coefficient, whereas small gamma is used for the propagation constant. And when I use the term gamma, means the propagation constant is complex, so it may be lossy. This transmission line may be lossy. Okay, so now what is this v minus of 0? V minus of 0 is the value of v minus of x at the source. So v minus of 0 is here. It represents the amplitude of the wave traveling in the negative x direction at the source, and v plus of 0 is the amplitude of the wave traveling in the plus x direction at the source. So gamma, so similarly we can write v plus of x as equal to v plus of 0. This comes from transmission line, solution of the transmission line equations, and gamma of x is then given by v minus of 0 upon v plus of 0 e raised to plus 2 gamma x. Okay, now so if on the other hand, so this is for a lossy transmission line. If the transmission line is lossless, then this will reduce to okay. So this is in terms of x, but what will the value of gamma be in terms of L? So let us consider this equation once again. Gamma x is equal to v minus of 0 upon v plus of 0 e raised to 2 gamma x. Now suppose again, if I once again bring back d, which is the distance of this point from the load end, okay, and we have d is equal to L minus x. Conversely, x is equal to L minus d. So if we now substitute this value of x in this equation, then gamma of d will be equal to v minus of 0 upon v plus of 0 e raised to 2 gamma L minus d, which in turn I can write it as v minus of 0 e raised to gamma L upon v plus of 0 e raised to gamma L e raised to minus 2 gamma d. Okay, now what is this value?